Hello. Today we will learn about the analyze a system response in the time domain. And you will be able to use the mathematical tools such as differential equations and convolution when you want to analyze a system response, especially in the time domain. So we know this thing that there are two methods of analysis of linear time invariant system, that is the time domain method and frequency domain method. But today we will focus on only linear differential systems, the class of linear time invariant system for which the input x of t and output y of t are related by linear differential equation. So when we consider differential equation of the form like this, where all the coefficients ai and bi are constant, okay, like here a1 and then so on till an, and your here a naught. So we obviously, if it is here 0, so we will not mention it. Then we can say using operator notation d to represent d over dt, we can express this. So derivation, we can replace this thing like this part only with a d if we write. So what will happen, that we can write in this way, like if we are taking y of t common from here, from here, and the other part, that is the derivation part, we can write in the form of d. So here d raised to the power n, then d raised to the power minus 1, and so on. So we will get this left hand side, and the same thing if we apply on the right hand side. So you can see over here, this is the part of the derivation, and then x of t, this is the part of the derivation, and then this is x of t. X of t we have taken the common, and then we can write them d raised to the power m, d raised to the power m minus 1, and so on. And here n minus m, so here n minus m plus 1, and so on. So obviously here m will become equal to n, so it will become 0, so we will not mention the m here, no m, n minus 1, and then obviously m is 0, so here no. So we can express this as the polynomials qd y of t pd x of t. So this is the input and output. Like practical systems generally use m less than or equal to n. So here, for generality, we can say is we can assume m equal to n. Now, as the system is linear, its response can be expressed as the sum of two components. Remember, linear system. Now we know the characteristics of linear system. There are two properties that linear system satisfies: the additive property as well as the scaling property. So as these two properties are satisfied by the linear system, so we can express its response as the sum of two components: zero input response and zero input and zero state response. Now what is the difference between them? Basically, system output, zero input response. Right now we are talking about zero input response. So it's mean there is no input. Zero input means no input. So if there is no input, so basically system is depending upon its initial conditions. What were its initial conditions? So we can say this thing, that if input x is t equal to 0, and thus it is the result of internal system condition that you are getting some y of t out. And if we say zero state response, so zero state response means that there is no internal initial condition of the system. The all initial conditions are 0. So we can say this thing, that the system output to the external input x of t, the output that you are getting from the system is just because of that input that you are giving. There is nothing inside, nothing initial condition. When the system is in zero state, meaning the absence of all internal energy storage, there is no internal energy storage. So very simple, we can say this thing, Zero input means you the output is because of the internal storage of the system. Zero state response means the output of the system is because of the input and there is no internal storage. Zero input response means that input is nothing. Whatever you are getting from the system is because of its initial conditions, because of its internal energy storage. So after this, now we can see the system model. The zero input response is the solution of output when the input x of t is zero. So if obviously input is zero, so here we can write zero now. And then this is the system response. And this response is depending upon the system initial conditions, its internal energy storage. There is no input. So we will get this equation. Now, this system response is to internal condition. And we know that the solution is an exponential function, so we can write in this lambda t. So, output can be expressed as there is some constant, the output, this is the response or the output of the system. So, this is the constant e raised to lambda t. So from the first equation 1, if you see here, okay, like these are the derivatives, no, basically till here. We can write in this way. Like if on a 0, so we will have the derivative. If we take the derivative, and this is the constant e raised to the power exponential function, and we take the derivative, so whatever is here in the power, it is multiplied by this constant, and then we again take the derivative, so it is again multiplied, so there are two lambdas, so it will become lambda square, and then so on till here we get n, so it's mean we will have here n lambdas. Okay, so we can write this side, the right hand side, in this way, like if we can take the c common, and then we can take the sum of all these. So what we will get, we will get lambda n, and so on, and e raised to the power lambda t, that is also common here, like I changed my color, like here here, so I can take the common both things, no? Because this is common. And if I write all the internal, so I can take the sum of this all lambda n, and then there is some constant, and then so on. That is equal to 0. So in this way, I can solve the equations as well. So in factorized form, we can write lambda minus lambda 1, lambda minus lambda 2, and so on till lambda minus lambda n. So this q of lambda is the characteristic polynomial of the system, and this q equal to 0 is the characteristic equation. So sometime in the exam, characteristic equation and polynomials are also asked. Now, zero input response, they are further giving the detail, and these are the key points about the characteristic mode, that the exponentials like this in the zero input response are the characteristic modes, also known as natural modes or simply as modes of the system. There is a characteristic mode for each characteristic root of the system, and the zero input response is a linear combination of characteristic mode of the system. This is very important point. What is the zero response? Zero input response is a linear combination of the characteristic modes. And what are the characteristic modes? These exponentials. These are the characteristics modes. Just you are going to combine them. So you are able to get the zero input response. So a linear time invariant system characteristic modes comprise its signal most important attribute. Characteristic modes not only determine the zero input response but also play an important role in determining the zero state response. Yes. So these characteristic mode is important, like how you will able to find this. Then zero input response as well as zero state response, you will be able to find out. So we can say this thing, that the entire behavior of the system is dictated primarily by the characteristic mode. So it is important for you to know how to find the characteristic mode with the help of characteristics roots. And then, like this, we can solve that. Now in this example, we have to find the output, the zero input response of the response. Obviously, if there is no input, so we can, this is the output, so we can simply write the equation y of t equal to 0. And then we need to find the roots. So as we can, like the initial conditions are given to us, as there is no input. So if we have y 0 0 and we take the derivative, see the dot derivative, so it is -5. These are the initial conditions that are given to us. Now using these initial conditions, and if we solve, so first we can replace the d with a lambda characteristic equation. And then if we make the factor, so we can write like we have x 3 lambda plus 2. So by mathematically we can make the factor lambda plus 1 and lambda plus 2, that is equal to 0 over here. So from here, what roots we will get? From this part, lambda equal to -1. From this part we can get lambda equal to -2. Now in order to find the characteristic modes of the system, we will have e raised to the power minus t and e raised to the power, because if you remember, e raised to the power lambda t. So what is lambda? Here lambda 1 is -1, okay, minus t, and the other -2, okay, e raised to 1 minus 2. And you just need to combine them, you just need to add them, combine, and you know the constant c1 and c2. So you will, this is your zero input response that you are getting from the roots and mode of the system, characteristic mode. This is characteristic mode, or simply modes we can say, or natural modes also we can say. After this, yes, if we can solve it further, but this is just if we want to find the c1 and c2. So to determine the constant c1 c2, we set equal to 0 in the equation, and the initial conditions were given to us. So according to initial condition, we know this thing, that we are getting 0 and -1, where we have c1 and c2, and the other case where we are having lambda equal to -1 and lambda equal to -2, okay, like this. So it is -5. So by simply solving mathematically, like how we can solve 0 and -5, that is equal to minus c1 minus 2 c2. Here it is c1 plus c2. So if we add both of them, so what we will get? Here it is cancel out. So here we will have minus, because this is -2, this is 1. So -2 plus 1 will give us -1. So -1 C2. This minus minus cancel out. It means C2 is equal to 5. And if we have C2 equal to 5, we can put in any equation to get the C1. So let's suppose we put C2 in equation number 1. So we will have 0 equal to C1 plus 5. So it means C1 equal to -5. So we are able to find the coefficient C1 and C2 as well. Now the equation for the zero input response we have here, we can just put -5 plus 5 in a, and the rest of the part we have already solved over there. Here, this is the equation after taking the sorry, this is the equation, actually not the derivative, this is after the derivative, this one. Okay, so repeated roots, yes, the solution given by we can have in this form, like c1 c2 up till cn. And then similarly here is to the power lambda 1 lambda 2 till lambda n. Assume that n characteristic roots are distinct. So repeated roots of the characteristic modes can be described in this way, and the solution is like this, very easy. Like you have the constants outside it by taking it common. This is the second example. This is also in the same way, but what is the initial condition over here? One derivative, two derivative, that is equal to one. So question from you, what are the characteristic roots of this system? And determine the zero input response. So in order to determine the characteristic roots of this system, you just have to write this. Instead of d, write lambda here, write lambda square, and make it equal to 0, because zero input is nothing. So this is the equation that we get. Then we solve this part in by mathematical formula, that is a square minus b square, that is equal to a plus b and a minus b. So we can write in this way. So from here the repeated roots that we have find. So if we have this one, this part, so plus 1 equal to 0, then this part plus 1 equal to 0, then this part, then y minus 1 equal to 0. So if we see here 1, 2 and 3, so here we are getting minus 1 and plus 1. So it's mean lambda 1, lambda 2 are equal to minus 1 and lambda 3 is 1. After finding these repeated roots, because characteristic roots of the system we need to find. So now we are moving towards determining the zero input response. So these are the initial conditions that were given to us. One time derivative, then second time derivative. Very simple. If we take the first time derivative, it's mean c1 e raised to the power t plus c2 t, because obviously what is over here, when you will apply the derivative, it comes here minus 1, so minus 1 here. But here product, you will use the product rule of integration. So what is the product rule of derivation? Simple, but we can have c2 te minus t. It's mean you are having c2, this minus sign here. So minus t e raised to the power minus t plus the second part e raised to the power minus t. Okay. And then the third one, like here. Then you again take the derivative. So minus minus will become plus. And then here again you take the derivative. So you will be able to take this minus here. So minus minus will become positive. And again the product rule apply, like t e raised to the power minus t. It's mean you will take the derivative of t as well as you will take the derivative of e raised to the power minus t. So two times like this you will have e raised to the power minus t. Then simply you will by the initial condition, it was given to us that it is all equal to 1. Like here you can see in the question it was given here. If we take these derivatives, so we will have all these equal to 1. So we have written it 1, and then we simply solve these equations to find the constants. So you can use any method to find these constants. So simply, if you want to write in the form of complex number, so this is you are having the zero input response by comprising a single no mode e raised to the power t only. Okay, if you put c1, c2 and c3 in the values, so here we have 0 0 and 1, so we will get this. And then we can further write in the form of complex roots. So we will get c e and then we can describe it. This is another example that is given to us in the description. I will mention this example as well. So there are some examples that are further about the unit impulse response. So next time we will continue this. Okay, then take care. Bye.